Hello again, everybody. Welcome back to Intermediate Algebra. Today we are in section 10.5, which is our very last section, and this section is all about multiplying and dividing rational expressions. So today I'm going to show you how to multiply radical expressions, how to rationalize denominators when there's one term in the denominator, how to rationalize denominators when there are two terms in the denominator, and also we will practice writing radical quotients in lowest terms. So let's go ahead and get this one last lesson started. Okay, first you'll be glad to know that the distributive property is still used the same way when you're multiplying radical expressions. So let's practice here. We have square root of 5 times 2 plus square root of 6. So we just want to distribute this square root of 5. So when we multiply a radical times an integer, typically we write the integer in front so that there's no confusion about whether that number is under the radical or not. So square root of 5 times 2 will be written as 2 square root of 5. And then we will be multiplying square root of 5 times square root of 6. And we know from our product rule for radicals that that's going to be square root of 30. So final answer here, 2 square root of 5 plus square root of 30. In part B, we have 4 times square root of 12 minus square root of 27. Now, you could go ahead and distribute the 4, but I think what I would prefer to do is simplify these radicals first. So let's think of 12 as 4 times 3, and let's think of 27 as 9 times 3. So we'll have 4 times the square root of 4 times 3 minus the square root of 9 times 3. So the 12 is the 4 times 3 and the 27 is the 9 times 3. Now we will use the product rule for radicals to simplify this, but we are not going to write the step where we have the 4 under a radical and the 3 under a different radical. We're just going to go ahead and simplify. So we're going to skip writing out that one step. So this is going to now be 4 times 2 times the square root of 3, because the square root of 4 is 2, minus 3 times the square root of 3, because the square root of 9 is 3. So you see how that works? And what we did was we just did not write the step where each number is under its own radical. Now we could either choose to distribute the 4 at this point, or we notice that inside the parentheses these two radicals are the same, so we're going to be able to combine these into one term. So I'm choosing to do that first. So 2 square root of 3 minus 3 square root of 3 would be negative 1 square root of 3. That leaves us with 4 times negative 1 square root of 3, which is just negative 4 square root of 3. Now we can also use the FOIL method to multiply binomials that contain radicals. So it works exactly the same as it did when we didn't have radicals. It's just first, outer, inner, last. So here we go on part A. First times first here would be square root of 5 times square root of 6. So we know that that's going to be square root of 30. Then outer times outer would be square root of 5 times 1. So of course that's just square root of 5. Inner times inner would be 3 times the square root of 6. And last times last would be 3 times 1. So that's just 3. Now, if any of these radicals could be reduced, we would have to do that. If any of these terms could be combined, we would also have to do that. But in this case, the square root of 30 cannot be reduced because 30 is just 5 times 6 and there are no perfect square factors there. Of course, 5 and 6 cannot be reduced, and there's really nothing here to reduce or combine, so this is the final answer for part A. Now let's look at part B. So again, we have a binomial times a binomial, so we would need to use the FOIL method. First times first would be 7 times the square root of 5. Outer times outer would be 7 times the square root of 2. Inner times inner would be negative square root of 3 times the square root of 5. And we know that 3 times 5 is 15, so we're just going to write this as minus square root of 15. And then last times last would be negative square root of 3 times square root of 2, so we will write that as minus square root of 6. Now, just like we saw in part A, if any of these radicals could be reduced, we would have to do that. And if any of these terms could be combined, we would have to do that. but all of these radicals are different and none of them can be reduced, so nothing can be combined here, and this is our final answer on part B. Now in part C, we're using the same method. We will still multiply using the FOIL method, but notice something here. These two binomials are closely related. Here we have square root of 10 plus square root of 3, and here we have square root of 10 minus square root of 3. So when we multiply these together using the FOIL method, watch what happens. Square root of 10 times square root of 10 is going to make just 10. Outer times outer is square root of 10 times negative square root of 3, so that's going to make negative square root of 30. Inner times inner is positive square root of 3 times positive square root of 10, so that's going to make positive square root of 30. And last times last is positive square root of 3 times negative square root of 3. So positive times negative gives us a negative, and square root of 3 times square root of 3 gives us 3. So this is what we've ended up with. Now notice that because the first term in each parentheses is the same, when we multiply those together we lost our radical. And the same goes for last times last. We lost our radical. And notice that because outer and inner are giving us the same value but with opposite signs, those two are going to add up to 0, and then 10 minus 3 is 7. So this is always going to happen whenever we multiply together a sum and difference of the same two terms. The radicals are going to cancel each other out, and we're going to be left with a rational number. Let's look at part D, which is a little different from C. In C we had a sum and difference of the same two terms. In D we have square root of 7 minus 3 squared. So that is square root of 7 minus 3 times itself. This time we do not have opposite signs here because we're squaring this binomial. So let's still go through the FOIL method and see what happens. Square root of 7 times itself is going to make 7. Square root of 7 times negative 3 is going to make negative 3 square root of 7. On the inner times inner, negative 3 times square root of 7 is just that. And on the last times last, negative 3 times negative 3 is positive 9. Now this time, these two middle terms do not have opposite signs, so they are not going to cancel each other out. But we can combine our first and last terms, so 7 plus 9 is 16, and then negative 3 square root of 7 minus 3 square root of 7 adds up to negative 6 square root of 7. And here is part E. So again, binomial times binomial, we'll use the FOIL method. First times first is 4 times 5, so that's going to be 20. Outer times outer is going to be 4 times the cube root of 3. And then inner times inner is going to be negative cube root of 3 times 5, so we'll put the 5 in front. And then last times last is going to be negative cube root of 3 times positive cube root of 3. Now, when we multiply a square root times itself, it removes the radical. But here we have a cube root times itself. So here the radical is not going to get removed, but we will multiply the 3's together. So negative times positive makes negative, and cube root of 3 times cube root of 3 makes cube root of 9. Now remember, to simplify a radical that is a cube root, we need a third power under the radical, and we don't have a third power. We have a second power. So that's why this radical won't reduce. But we do have two like terms here. The 4 times the cube root of 3 minus 5 times the cube root of 3 will combine to make one term. 4 minus 5 is negative 1. So we're going to end up with 20 minus 1 cube root of 3 minus cube root of 9. And that's our final answer here. Although you can eliminate this 1 if you want to, you can just choose not to write that coefficient, and that actually probably is best. Okay, let's try part F. So notice again we have a sum and difference of the same two terms. And they're telling us here that A and B both have to be greater than or equal to 0 so that we don't have to worry about taking the square root of a negative. But this is not going to affect how we work the problem. So we're still using the FOIL method, and we'll say first times first is square root of A times itself. So that's going to be A. And notice that I don't have to worry about absolute value bars because I've already been told that a is not negative. Okay, now on outer times outer, we have square root of a times negative square root of b. That's going to be minus square root of ab. On inner times inner, we have square root of a times square root of b. So that's going to be positive square root of ab. And then for last times last, positive times negative makes negative, and square root of b times itself makes b. So our last term will be negative b. Now notice that because we have a sum and difference of the same two terms, our outer and inner terms are going to cancel each other out, and we are just left with a minus b. Okay, now we are going to move on and talk about how to rationalize denominators with one term. So let's talk about what it means to get a radical expression simplified. A simplified radical expression never has a radical in the denominator, and it also never has a fraction under the radical. So whenever we have a quotient that has a radical in the denominator, it's our job to remove the radical, and that is called rationalizing. Because remember, if a radical can't be simplified away, then that radical represents an irrational number. So the process of removing the radical from the denominator is called rationalizing, because we end up with a rational number in the denominator. Now, if the denominator only has one term, then we can rationalize by using the fact that any radical divided by itself is 1. So let's see how that works in the next example. So in example 3, it says rationalize each denominator. Remember, that just means write this fraction in a form where we don't need a radical in the denominator. So we have 3 over square root of 7. So we're going to eliminate this radical by taking advantage of the fact that square root of 7 times itself is just plain 7. But if I multiply the bottom by square root of 7, I also have to multiply the top by square root of 7. Now notice, remember, this is allowed because any quantity divided by itself is 1. So what I have here is this thing times 1, but it's going to let me eliminate the radical from the denominator. So 3 times the square root of 7 is just that, and then square root of 7 times itself is 7. Now if we could reduce this radical, we would have to do that, and if we could reduce this fraction, we would also have to do that, but in this case, this answer is fully simplified. Now let's look at part B. So we have 5 times the square root of 2 divided by the square root of 5. And remember, we want to just remove the radical from the denominator. See, it says rationalize the denominator. So I'm going to, again, take advantage of the fact that square root of 5 times itself is 5. So I'll start with my original expression, and I'll multiply top and bottom by square root of 5. Now, in the top, 5 times the square root of 2 times the square root of 5 is just going to be 5 times the square root of 10. And in the bottom, square root of 5 times itself is 5. And now notice that we have a 5 in the top and a 5 in the denominator, so those will cancel each other out, and we're just left with square root of 10 for our final answer. In part C, we have negative 6 divided by the square root of 12. Now, you know that the square root of 12 is a radical that can be reduced, and we could choose to reduce the radical first, or we could choose to rationalize the denominator first. Neither choice is wrong. I prefer to rationalize first and then do all my simplifying at the end, but that's up to you. So I'm going to go ahead and eliminate this radical in the denominator by multiplying top and bottom by square root of 12. That gives me negative 6 square root of 12 for the top, and in the denominator, square root of 12 times square root of 12 is 12. Now again, I could go ahead and reduce this fraction, but after I reduce the radical, I might have to reduce the fraction again. So what I'm going to do is now choose to reduce the radical, and then I will do any reducing of fractions that is still left to do. So we know that 12 is 4 times 3. And we know that the square root of 4 is 2. So we're going to end up with negative 6 times 2 times the square root of 3 in the top, and in the bottom we have 12. Now we know that negative 6 times 2 is negative 12, and we have 12 in the denominator. So this 6 times 2 is going to cancel out this 12. Does that make sense to you? Because 6 times 2 is 12. So I just didn't write it over, but we can reduce like that. And I do have this negative left over here, so my final answer is just negative square root of 3. Now let's look at example 4. We're still rationalizing denominators. We're still asked to simplify here. So in part A we have negative square root of 18 over 125. Now remember that we said that a radical expression is not fully simplified if there is a fraction under the radical. So we need to split this radical up into two separate radicals, and that's going to give us negative square root of 18 in the top and then square root of 125 in the denominator. Now we could choose to simplify these radicals right now, and then you could rationalize. That would be fine. But I am going to do the same thing I did in the last example, which is go ahead and rationalize the denominator first. There's actually not any particular reason why. You could choose to simplify the radical first. I am just choosing to rationalize first. That's just a choice that I made. So I'm going to go ahead and multiply top and bottom by square root of 125. And you might be thinking, oh gosh, now we're going to end up with 125 in the denominator, and that's kind of a big number. And it is, but we would have to deal with it either way, so it's not going to make it harder to do this. Let's now go ahead and simplify both radicals. So we'll be multiplying the tops together and we'll be multiplying the bottoms together, but it's not going to be as much work as you think. We're not going to multiply 18 times 125 and get that giant number. What we're going to do is break these two numbers down. So we're going to think of 18 as 9 times 2. Don't lose your negative here. So we'll have negative square root of 9 times 2, and then I'm going to multiply that by square root of 25 times 5, because 125 breaks down into 25 times 5. Now in the denominator, I have square root of 125 times itself, so that gives us just 125 in the denominator. Now let's see what we can do about simplifying these radicals in the top. Again, don't lose your negative. So we have negative square root of 9, which is 3, times the square root of 2, times the square root of 25, which is 5, times the square root of 5. And then in the denominator, of course, our 125. Now, I could multiply 3 times 5 together and get 15, but there's no need to do that because I know I'm going to be able to cancel a 5 from the denominator. So what I'm going to do is just rearrange this top a little bit. I'm going to have negative 3 times 5 times the square root of 2 times the square root of 5. Now we may as well go ahead and put these two together under the same radical because nothing else is going to reduce from there, and that's going to give us square root of 10. In the denominator, 125 is again 25 times 5, and now I can cancel out these 5's, and we will be left with negative 3 square root of 10 over 25. And since this fraction will not reduce, we're finished here. Okay, in part B, again, we have this quantity under the radical, and we could do a little simplifying right now, but what I'm going to do is actually just split it up and do my rationalizing first and then my simplifying. There's, again, no reason for that choice except that it's just a personal choice. Okay, so I've written square root of 50m to the 4th in the top, and I have square root of p to the 5th in the denominator, and I'm going to rationalize this by multiplying top and bottom by that bottom radical. Now, let's go ahead and split up our factors in the top. So 50 is going to give us 25 times 2. There's no need to split up m to the 4th because that exponent is even. And for p to the 5th, we're going to write that as p to the 4th times p. In the denominator, square root of p to the 5th times square root of p to the 5th is just p to the 5th. So again, a square root radical times itself removes the radical. Now let's simplify these radicals in the top. So the square root of 25 is 5. The square root of m to the fourth is m to the second. And the square root of p to the fourth is p to the second. And this 2 and this p will both stay under the same radical now. And then we have p to the fifth in the denominator. So the only thing we can reduce here is these p's. So think of it this way. We have 5 p factors in the denominator and 2 p factors in the top. So these 2 p factors will cancel 2 of the p's from here, and that's going to leave us p to the third in the denominator. So now we have 5m to the second times the square root of 2p over p to the third. Have you noticed how we're using lots of skills here? We're using our exponent rules, we're using our radical simplifying skills, we're using our product rules and quotient rules. It all goes together. And now we're going to talk about rationalizing denominators where there's a binomial or 2 terms in the denominator. So if the denominator contains 2 terms, then instead of just multiplying top and bottom by the radical, we'll have to multiply top and bottom by the conjugate of the denominator. The conjugate is made of the same 2 terms but with the opposite sign between them. So for example, x plus y and x minus y are conjugates because the only difference is the sign in the middle. So what happens when you multiply a binomial times its conjugate is that the outer and inner add up to 0, and you'll be left with just first times first minus last times last, and there's no radical there because those are squared. So let's check it out here. We have square root of 5 plus square root of 3 times square root of 5 minus square root of 3. Now first times first is square root of 5 times square root of 5, so that's just 5. Outer times outer would be minus square root of 3 times 5, which is 15, so minus square root of 15. Inner times inner would be plus square root of 3 times 5, so that's plus square root of 15. And then last times last would be positive square root of 3 times negative square root of 3, so that's minus 3. Okay, notice that the outer and inner are going to add up to 0 because they're the same but opposite. And then 5 minus 3 is going to make 2. So that's how that always works. When you multiply a binomial times its conjugate, if it contains radicals, that eliminates the radicals. So we're going to see that here. It says rationalize each denominator. Remember, when they say rationalize the denominator, they basically mean write it so that there's no radical in the denominator. So the way we do that here, where we have 1 plus square root of 2 in the denominator, is we're going to need to multiply this by 1 minus square root of 2. But if we do it to the denominator, we have to also do it to the top. Now, I went ahead and put this first fraction in parentheses just to show that it's this whole fraction times this whole fraction. So what we're going to do now is top times top and bottom times bottom. So just distributing this 3 through the top. 3 times 1 is 3. And 3 times negative square root of 2 is just that. And in the denominator, first times first is 1. The outer and the inner are going to add up to 0, so there's no need to write that down. We already know in advance they're going to add up to 0. And then last times last is positive times negative, so it's going to be minus square root of 2 times itself, so that's a 2. So 1 minus 2 in the denominator. Now 1 minus 2 is just negative 1. And so when we divide each of these terms by negative 1, 3 divided by negative 1 is negative 3, and negative 3 square root of 2 divided by negative 1 is plus 3 square root of 2. And so that's fully simplified there. In part B, we have 5 over 4 minus square root of 3. So remember, if we need to rationalize a denominator with 2 terms, we'll have to multiply top and bottom by this conjugate. So we'll have to multiply top and bottom by 4 plus square root of 3. Now again, in the top, we're just distributing the 5. So 5 times 4 is 20, and 5 times square root of 3 is just that. And in the denominator, 4 times 4 is 16. Outer plus inner would add up to 0, but negative square root of 3 times positive square root of 3 is minus 3. Now, 16 minus 3 is 13. If there were any way to simplify this radical, we would have to do that. If there were any way to factor something out of the top and reduce, we would have to do that. But 25 and 13 do not have any common factors, so this answer is complete. In part C, now we have square root of 2 minus square root of 3 all over square root of 5 plus square root of 3. And so we are going to rationalize this denominator by multiplying top and bottom by the conjugate of the denominator. That's always the strategy. Multiply top and bottom by the conjugate of the denominator. So here we go, FOIL method in the top. Square root of 2 times square root of 5 is square root of 10. Outer times outer is square root of 2 times negative square root of 3, so that's minus square root of 6. Inner times inner is negative square root of 3 times square root of 5, so that's minus square root of 15. And last times last is negative square root of 3 times negative square root of 3, so that's positive 3. In the denominator, square root of 5 times square root of 5 is 5. These are conjugates, so outer plus inner is going to add up to 0. No need to write those out. And last times last is minus 3. Now all that's left to do is say 5 minus 3 is 2. Notice that nothing in the top will combine, but I am going to write this integer first as the first term. There's no real rule that tells me I have to do that. It just kind of looks nicer that way, I think. So I'm going to put 3 plus square root of 10 minus square root of 6 minus square root of 15. None of those can be reduced or combined. And then in the denominator, 5 minus 3 is 2. And so this answer is fully simplified. And now let's look at part D. We have 3 over square root of 5m minus square root of p. So again, we have two terms in the denominator. In order to rationalize this, we'll have to multiply top and bottom by the conjugate of that denominator. So in the top, all we have to do is 3 times this quantity. I'm not even going to distribute the 3 this time. I'm just going to write it like this. And in the denominator, square root of 5m times square root of 5m is 5m. Outer and inner are going to add up to what? 0. You guessed it, because these are conjugates. And then last times last is negative p, because square root of p times square root of p is p. Okay, now there's nothing we can do to combine or simplify that. In the top, you could distribute this 3, but it's really not necessary. There's no rule. You know, as long as you're dealing with all numbers, I think it's customary to go ahead and distribute. But here, where we have variables, sometimes you do and sometimes you don't, and there's no real rule why you have to do one or the other. But the reason I didn't want to distribute it first is really because I was hoping that something might reduce, but of course it didn't. So we could either leave it factored or go ahead and distribute. Either way is acceptable. And finally, our last example of the last section in the whole course. So in this example, we're going to be writing radical quotients in lowest terms. Now, what you have to remember that you learned in Chapter 6 is that when we reduce fractions, we can never cancel terms, remember? In order to simplify, there must be a common factor in both the top and the bottom. So here where I have 6 plus 2 times the square root of 5, now some people would be tempted to add 6 plus 2 and get 8. No. 6 and 2 square root of 5 are not like terms, so they cannot be combined. But also, some people would be tempted to cancel the 6 and the 4, like reduce with the 6 and the 4, but you can't do that. What you have to do is factor a 2 out of the top and then reduce with factors. So if we factor a 2 out of the top, then in parentheses we're going to have 3 plus 1 square root of 5. Notice I did not write the 1, it's not necessary. In the denominator, 4 is 2 times 2, and I wrote it that way so that you can see that now we're going to cancel those 2's, and what's left is 3 plus square root of 5 in the top, all over 2. This 2 right here. Okay, let's look at part B. So in B we have 5y minus square root of 8y squared all over 6y. Now I'm sure the first thing you notice is that this radical needs to be reduced. So we're going to think of 8 as 4 times 2 And of course, y squared has an even exponent, so there's no need to break that down. And when we simplify this radical, in the top we will have 5y minus 2y, and this 2 will stay under the radical. So the square root of 4 is this 2, the square root of y squared is this y, and this 2 stays under the radical. And then in the denominator, of course, nothing has changed. Now notice that both terms in the top contain a y, so we will factor out a GCF of y, and in parentheses that's going to leave 5 minus 2 times the square root of 2, and the denominator is 6y. Now we can simplify the fraction, and notice that we have y in the top and y in the bottom, and so that's going to give us in the top 5 minus 2 square root of 2, and in the denominator 6. And for part C, we have 3 plus 5 square root of 2 over 6. Now notice that nothing will factor from the top. This radical cannot be simplified. 5 and 3 do not share any common factors. So although it may be tempting to reduce this 3 and this 6, you cannot do it because this 3 is a term of the top. This 3 is not a factor, it is a term. So it cannot be used to reduce this fraction, and we'll just have to say that this one cannot be reduced without splitting into two separate terms, which we were not asked to do. So we're just going to say this one cannot be simplified. And that's it, guys. If you've made it all the way through intermediate algebra, then congratulations, you have worked really hard, and I hope that it has paid off for you and that you'll be able to do well in college algebra next semester. Good luck, and thanks for all your hard work, and we hope to see you again next semester in college algebra. Bye.